How did Earth get its atmosphere? We are living a very long period on Earth. We often don't even notice some things that are keeping us in life that have always been there for us. We've been here so long, and we rarely think about necessary things. Instead, some nonsense preoccupies our minds. Have you ever looked up at the sky, taken a deep breath, and wondered, what are these things that surround us? Where did our atmosphere come from? What is our atmosphere really is? Well, hold on. You will get answers to all your questions in this video. Okay, let's start from the beginning. Earth was basically a huge ball of molten lava long ago when our solar system was developing into the planets we see today. Scientists estimate that Earth collided with a planet the size of Mars around 4.5 billion years ago. The force from this devastating impact melted the whole planet, produced our moon, and hurled Earth's atmosphere into space. With the emission of gases like nitrogen, hydrogen, carbon, and oxygen throughout time, this global magma ocean produced the earliest form of the atmosphere we know today. So what precisely was the environment like back then? And why has our atmosphere changed so much since it was last compared to our galactic neighbors? This new research suggests that Earth's early atmosphere was high in carbon dioxide and nitrogen, which would make it more challenging for these amino acids to develop. These tests also contributed to a better understanding of why the atmosphere of Earth now differs so greatly from that of our nearby planets. This magma-created atmosphere on Earth led to the formation of liquid water, which drew carbon dioxide from the atmosphere and into the planet's developing seas. It was the combined effects of the Earth's large mass and its particular distance from the Sun, according to Sosi, now a senior research fellow at Eidgenössische Technische Hochschule ETH Zurich and the National Center of Competence in Research NCCR, Planet S, that allowed it to retain liquid water on its surface, which then caused a carbon dioxide drawdown. This is because all three planets, Earth, Venus, and Mars, were formed from similar materials. On Venus, however, it was too hot, and on Mars, it was too cold, so that wasn't the case. One mystery explained. Now, we move on to others. Evolution of the atmosphere. Although the method by which the present atmosphere evolved from past circumstances is complicated, there is a wealth of indirect evidence for this evolution. The atmospheric composition has changed in the past as a result of chemical interactions with the Earth's crust and, in particular, with biological processes related to life, according to ancient sediments and rocks. The initial atmosphere of Earth was deficient in free oxygen, but abundant in methane, ammonia, water vapor, and the noble gas neon. The initial biological generation of oxygen by unicellular organisms and its final buildup in the atmosphere most likely occurred hundreds of millions of years apart. A considerable lot of information about the atmosphere's origin is encoded in its makeup. A further indication of the significant interconnections between the atmosphere, terrestrial environment, and biota is the nature and variability of the minor components. We all have some kind of evolution, but hardly anyone can boast of it like planet Earth. Now, we will take you through some more steps as it gradually comes to this. The sequence of events in the development of the atmosphere, absence of a captured primordial atmosphere. The planet should have caught an atmosphere made out of nebular gases if it became massive and hence had a strong gravitational field, before all the gases left its orbit. Such an atmosphere's size and makeup would be influenced by the planetary mass and temperature. The minimum molecular weight that could have been retained if the solid planet had grown to its full size and at temperatures higher than 2000 degrees Kelvin may have been so high that the extremely abundant gases with molecular weights between 10 and 20, methane, ammonia, water, and neon, would have been collected ineffectively. Yet it still should have been possible to capture a thin, primordial atmosphere made up of nebular gases with larger molecular weights, like argon and krypton. Despite this, features of the current atmosphere plainly demonstrate that a primordial atmosphere either never existed or was entirely lost. Both of these options have explanations that relate to the sun's growth. Astronomical observations of developing stars have revealed that these stars' early histories are characterized by periods in which the pressure of light and particles ejected from the stars as they turned on, causing the gas in their surrounding nebulas to be blown away. It would have been impossible for Earth to retain a primordial atmosphere if the removal of gases took place in the solar system after non-volatile minerals had condensed, but before the inner planets, Mercury, Venus, Earth, and Mars, accreted. Alternately, if the gas ejection was preceded by planetary accretion, and Earth had accumulated a primordial atmosphere, it's possible that the early solar radiation, in particular the solar wind, was so intense that it was able to completely remove all the gases from the inner planets, fulfilling the second requirement outlined above. After the primary, we move on to the secondary, which will leave you speechless. Secondary atmosphere. The phrase secondary atmosphere refers to the atmosphere that formed following the loss or failure to accumulate of the primordial gases. The inventory of volatile elements on which the atmosphere is based has not changed, despite the fact that the chemical makeup of the atmosphere has changed significantly over the billions of years since its origin. Although you probably thought that the atmosphere was from one part, well, you were wrong. Now we will go through it part by part to make it easier for you. Layers of the atmosphere. Each layer in the Earth's atmosphere has unique characteristics. These layers, which rise from the surface of the Earth, are known as the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. With time, the exosphere eventually disappears into interplanetary space. The base of our atmosphere is called the troposphere. It begins at ground level and rises to a height of approximately 10 kilometers above sea level. Almost all weather happens in the troposphere, where we, as people, reside. Because the troposphere contains 99% of the atmosphere's water vapor, here is where the majority of clouds form. When you go higher in the troposphere, the air pressure decreases and the temperatures decrease. The stratosphere is the layer above that. From the tropopause to roughly 50 kilometers above the surface, the stratosphere is present. The stratosphere contains the famed ozone layer. High-intensity UV radiation from the sun is absorbed by ozone molecules in this layer, which turns the UV energy into heat. In contrast with the troposphere, the stratosphere actually warms up as it ascends. The stratosphere's air lacks the turbulence and updrafts that characterize the troposphere below due to the tendency of rising temperatures with altitude. Commercial passenger planes travel in the lower stratosphere because it offers a smoother ride and has less turbulence. The troposphere-stratosphere boundary is where the jet stream passes. The mesosphere is located above the stratosphere. It rises to an altitude of around 85 kilometers above our globe. The mesosphere is where most meteors burn up. When you ascend into the mesosphere, temperatures drop once again, in contrast to the stratosphere. Towards the top of this layer, temperatures as low as -90 degrees Celsius are recorded in the Earth's atmosphere. The air pressure in the mesosphere is far too low to allow for breathing. It starts off at far below 1% of sea level and becomes lower as you go higher. The thermosphere becomes heated to hundreds or even thousands of degrees by the sun's high-energy X-rays and UV radiation. But because of how thin the air is, we would experience extreme cold in this stratum. The thermosphere resembles outer space in many aspects, more than it does the atmosphere. In fact, a large number of satellites circle Earth inside the thermosphere. The height of the top of this layer and the temperature inside it are strongly influenced by variations in the energy emanating from the sun. As a result, the top of the thermosphere is located between 500 and 1,000 kilometers above the surface of the Earth. The top thermosphere can reach temperatures of up to 2,000 degrees Celsius, or roughly 500 degrees Celsius. The thermosphere is where the aura, often known as the northern and southern lights, occurs. Despite the fact that some specialists believe the thermosphere to be our atmosphere's topmost layer, others believe the exosphere to be the final frontier of the planet's gaseous envelope. The exosphere is even more like space than the thermosphere because, as you might expect, the air there is extremely thin. In actuality, the exosphere is continually leaking out of Earth's atmosphere into space, albeit very gently. The exact top threshold where the exosphere ultimately vanishes into space is not known. According to several definitions, the exosphere's top is located between 100,000 kilometers and 190,000 kilometers above the Earth's surface. This figure is almost halfway to the Moon. Unlike the other layers discussed above, the ionosphere is not a discrete layer. The ionosphere, on the other hand, is a collection of places in some mesosphere and thermosphere where high-energy radiation from the sun has jarred electrons free of their parent atoms and molecules. The ionosphere gets its name from the electrically charged atoms and molecules that are created in this process. These ions also give this area some unique features. After spending so much time on this planet, we now finally know something more about it. Thank you for joining me on this journey, and stay tuned as we have only just begun. In the next video, we are preparing something even more interesting for you, so get prepared. Thank you for watching, and don't forget to hit that like and subscribe button.